Good afternoon. Let's continue with discussion of the BJT amplifiers and applications. So we had stopped at the load line analysis of a CE amplifier. And this is where we stopped, right? So we saw how the how the application of a small AC input signal at the base of a BJT can translate into an amplified output at the collector. Okay, let's look at what happens when the DC biasing might change. So this was the input on the left. You can see the scale is in millivolts, and the output on the right, scale is in volts at the collector. Now, the DC bias that we applied here in this circuit, let's see, was about, VCC was 10 volts, 10 volts biasing, right? So our output is between 3 and 7 within the confines of the VCC supply that we're applying. And that is due to biasing the operating point in the middle of the active region, which is right here. Now, let's say the first case of where our DC bias would not bias it in the center, would not center the operating point in the middle of the active region. Instead, let's say you started somewhere here, down there. So if your Q point, if your original Q point was down here, what do you think would happen? If your original Q point is closer to cutoff, then the positive peak of your output is going to get clipped or cut off. Okay, so as Q point shifts downwards, meaning towards cutoff, the positive peaks would start getting clipped. And that is because this positive peak is now closer to the cutoff region. And the same thing happens if your Q point is biased somewhere closer to the top. Yes. Yes, positive peak of the output. Yes. Yeah. Input is not affected. Input small, it's going into the BJT. But if your biasing does not center your Q point in the middle of the active region, your biasing point, your Q point might be either towards cutoff or it could be towards saturation. If it's towards cutoff region, then your output positive peaks start getting clipped, which is like right here, right? And if your Q point is up near the saturation region, then your negative peaks of the output start getting clipped. And so in both cases, what we observe would be distortion. And let's say, actually, towards saturation, clip, negative peaks. Okay. In both cases, the resulting is, we call the resulting waveform as distorted because it's not an exact replica of the input. Okay. It's not an exact replica of the input. Now, second case would be if the input signal is large. If the input signal is large to begin with, in the sense that instead of like 10 to 50 millivolts, it's now 100 millivolts, 200, 300, 500 millivolts signal, peak to peak. Then your waveform, your output waveform, can get clipped like this. And you may have observed or noticed this when we did the experiment in the lab for the BJT amplifier. When we provided a bypass capacitor across the emitter, the gain was larger. Because the gain was large, the signal is amplified more than without the capacitor. And so you could see clipping or distortion at the top and at the bottom. Let's say this was 10 volts, because that was the 10 volts VCC that we were applying, right? So if your gain is large, sorry, not gain is large, if your input signal is large, your amplified signal would exceed the bounds of the VCC signal, that's VCC voltage that's being applied. And in that case, both ends of the peaks, both ends of the waveforms would get clipped, which again is distortion. A real life example of this would be when you increase the volume of any audio device beyond the capabilities of the speaker or beyond the capabilities of the amplifier. And you would hear tearing sounds coming out from the speaker cone. And that's what is actually happening. Okay, that is what is happening. All right, any questions? Okay. All right, so we spoke about DC biasing, right? DC biasing. Now, in this circuit, we simply applied one single base resistor, and we had VCC and VBB applied on the collector and the base sides, right? The input and output sides. So DC biasing the transistor. We're not doing the analysis of the gain equation, right, for this circuit, but the end result of this kind of bias is that the amplification or the gain factor depends on the beta of the transistor. Okay, so this kind of DC biasing is known as fixed bias or fixed base bias, and it depends on the beta of the transistor. So if you had two transistors, again in your lab kit you have two transistors, one of them may have a beta of 35, another may have a beta of like 100 or even 150. So if the circuit works for a beta of 35 and you plug in a different transistor, the exact same model, make and model from the exact same manufacturer, but it would have a different beta, and the circuit would result in a clipped output waveform. Okay, so this is the first circuit in base biasing. Far more common is this kind of circuit. This circuit, in the book, is known as a self-biasing circuit, but more commonly it is known as a 4-resistor bias circuit, or even more commonly as a voltage divider bias. Okay, so this is known as a 4-resistor bias or a voltage divider bias circuit. And I'll quickly take you through the analysis of this. But the end result of this is that the Q point and the gain of the circuit does not depend on the beta of the transistor. Okay, so the beta does affect it, but the effects are minimized. Okay, and we'll mathematically see how that happens. So in this circuit, what you have is you have the standard resistors connected to the capacitor, emitter, sorry, to the collector, base, and emitter. So you have RC, RE, and RB. Okay, but in addition to that, the voltage to power the base or to bias the base does not come from a separate supply. It comes from the same VCC supply. And to achieve that, what we do is we create a voltage divider network. If you all recall from voltage divider network, any series connection of resistors, if you apply a voltage, the current remains the same, but the voltage gets divided in proportion to the ratio of those resistances. So if you look at the equivalent circuit here, you see there's a voltage that we are applying. That voltage comes from the VCC that is also on the collector side. So it's the same voltage on both the collector and the base side. right? Same voltage. And R1 and R2 create a voltage divider network. And so when you apply VCC, the actual voltage being applied to the base depends on the value of R1 and R2. Okay, those are the resistors that are connected at the base, which is also the circuit that we performed in the lab. So if you'll recall the BJT amplifier circuit, it had two resistors, RB1, RB2. Those correspond to these resistors, R1 and R2. Okay, they form a voltage divider network. So the voltage that is applied into the base is given as VAB. So it's a fraction of VCC. That fraction depends on the value of R1 and R2. Okay, so voltage divider network. I'm assuming, did you all study that in 115? Hopefully, yeah, right. Okay, so that's the voltage that's going in. Now, since we have two resistors in there, we can easily find the voltage, but we also need to find the equivalent resistance as seen by the base, right? We need to convert this circuit into this because the base sees only one resistor, RB, and we need to determine that resistor. That resistor is a combination of R1 and R2. Hence, we need to use a Thevenin equivalent circuit. We need to apply Thevenin's theorem to the input side and obtain RB, the value of this resistor, and the value of VBB. And VBB is something we just spoke about. VBB is basically this. That's the voltage that's going into the base, right? And then RB is basically the Thevenin resistance as seen from the perspective of the base. So that turns out to be R1 in parallel with R2, and you have RB as the parallel combination of R1 and R2. Okay, parallel combination of R1 and R2. And that's how we obtain this equivalent circuit. The output side is not affected. Output side, collector resistor, emitter resistor stays as it is. That is not affected. It's only the input side that you're using to bias with the same power supply. Okay. Let's take a short pause. Let me know if you have any questions. So far, so good. Okay. All right. So once we have the equivalent circuit, we proceed in the same manner. We apply KVL in the input and the output side. In this case, the intended goal of this slide or this page is to show students or display to students how we can obtain an equation for the output voltage, right? And so you're only looking at the output and the output voltage and the input voltage. At the input side, we have VBB, VRB, VBE, and the emitter resistor VRE. So you have 4 voltages on the input side. You modify that equation. So we have 1 voltage, 2, 3, and 4. 4 voltages on the input side. And then describe this current going in as IB, right? So we can replace VRB with IBRB. We can replace VRE with IERE. Now, this equation has already been developed by whoever designed this long time ago, right? So if you're approaching this as an engineer, as a new circuit that let's say you're analyzing, you're trying to design, you're trying to understand, what we are trying to achieve here is we want to obtain an expression for the output voltage. It could be output voltage or output current. It would be IC and or VCE on the output side in terms of the input parameters or the input quantities. Input quantities would be VBB, VBE, and or IB, and the output would be IC and or VCE. Okay, so we want to obtain an expression for IC or VCE in terms of VB or IB. So that's what we're trying to do. So when we applied KVL on the input side, we obtain this expression. We want to manipulate this equation such that we obtain the output quantities and the input quantities in the same equation. And then we rearrange the terms to obtain output is equal to some input quantity. And that's what we're trying to do here. And so once we have this IBRB and IERE plugged in there, we're going to rearrange the terms, obtain IBRB here, try and insert IC in there somewhere. So IE is equal to IC plus IB. And IC can be written as beta IB. And so IE is IB into beta plus 1. Okay, that's the standard expression. We plug that into the above equation and we obtain this step. Once we have that, we are going to manipulate and rearrange the terms. So we obtain the base voltages all on one side and then rearrange the terms to obtain an expression for IB. Okay, rearrange it to obtain an expression for IB here. Now IB or beta IB is IC. So if you want to go from IB to IC, we use that exact same expression. So IB is IC over beta. And now we have introduced IC into our equation. And once we have IC, we can rearrange the terms and now obtain this. That's my final equation for IC. Okay, IC is equal to VBB minus VBE. Those are the input voltages on the base side, right? So now we have output current as a function of the input voltages. Sorry, output current as a function of the input voltages. And at this point, we make an assumption. Assumption, approximation, anything works. Beta is typically large, far larger or far greater than the number 1. Okay. Even the 2222 transistor that we referred to in the lab, it had a lowest beta of 35. So even if you have a beta of 35, beta plus 1 over beta is going to be 36 over 35, approximately equal to 1. Make sense? Right? So beta plus 1 over beta would be approximately equal to 1. So we can write this as simply RB over beta plus RE. So this is gone. And that's an approximation. We don't have to assume anything. It's an approximation, right? So beta will affect it, but not to a large extent. I mean, the effect will be very minimal. And if we design and choose the values of our resistors such that RB divided by beta is far less than RE, then IC is simply dependent on the input voltages and RE. There is no beta in that final equation. Okay. There's no beta. It is there, but when we are designing, we are always designing with a purpose or a specific application in mind, right? We're always working backwards as an engineer. We have a goal and you always work backwards. So at the beginning of our analysis, not analysis, our design, if we choose RB such that RB over beta is far less than RE, then IC is not dependent on beta. the effects of beta would be very minimal or minimized. Okay. Let's take a pause. What do you think over that? Let me know if you have any questions. Any questions? Okay. One final point about this would be that if this beta varies 35 to 100, we have to account for that value too. It could vary from 35 to 200, let's say, right? 35 to 200. So within one single transistor line, beta could vary widely from 35 to 200, maybe from 50 to 300. So if that happens, we have to consider those values when we are choosing the values for RE and RB. Okay. RB is the parallel combination of R1 and R2. So the larger we choose R1, the smaller the effects of RB over beta. So we want RB to be as small as possible to begin with. Okay. And that would mean R2 should be far smaller than R1, which is here. This resistor R2, which is connected between the base and ground, should be smaller than R1. And then RB would be far smaller. And then RB divided by beta would be far smaller than RE. You can go back and check your amplifier circuits, and you can look at the values of the resistors that we used. And this would hold true to a large extent. Okay. And there is another derivation, which is not shown here, but it kind of follows the same path. And we can say gain of this circuit, anyone remember? Was approximately equal to the ratio of RC and RE. There's a small derivation about that too. So if anyone's interested, I can show them outside of class. But kind of follows the same path. AV would simply be output voltage to input voltage. And so if you rearrange the terms, you'd obtain approximately RC divided by RE. Actually, it would be negative minus RC or RE because it's an inverting amplifier. All right, time, so 1:58. All right, any questions? Okay. There's some large signal application amplifier that I wanted to go through, so I'll quickly go over these, and then we'll talk about this a little bit on Wednesday. So there are 4 applications. One of them is it's 4 applications of BJTs. Okay, BJTs. This one uses the diode temperature property, so diode thermometer measurements. The signal coming from the diode in response to the change in temperature be very, very small in millivolts. And so we use a transistor to amplify that signal so that at the output, that amplified signal can be used to indicate the temperature. So in this case, we're going to use the BJT as an amplifier in the active region. Next application is as an LED driver. LED is the light emitting diode. Light emitting diodes typically have a larger voltage drop in excess of 1.1 volts and requires at least 15 to 20 milliamps of current to turn on. If you have, let's say, a sensor in a system, the output of that sensor would typically be very small. Typically, it would be like millivolts or less, and it would not have enough current to drive an LED directly. Since it does not have that capability to drive the LED directly, we insert a transistor. The transistor is operated as a digital switch. That digital switch is controlled by a sensor. When the sensor output is 0, the transistor is cut off, so the LED is off. When the sensor output is high, or logic high or logic 1, the transistor turns on. even though there is a small base current, the power to turn the LED on or off the power to turn on the LED comes from the 5-volt external supply. The transistor acts as a digital switch and allows a pathway for the current to flow through. Another one is a battery charger. Similar application, depending on the bias and depending on the value of the voltage level of the battery, the transistor would turn on or off. And then lastly, it's a motor driver. Motors, DC motors, would require a large amount of current to flow through itself. And so we typically use transistors and MOSFETs to drive a DC motor. Okay, so this one's very interesting because it's a double transistor configuration. The output of one transistor goes as input into the second one. So the current amplification at the second stage is quite large, which is sufficient enough to drive and control a DC motor. All right, we'll end class here today, and we'll pick up here on Wednesday. Reading assignments were already posted, so please keep up with those so you'll be better prepared to engage with class next class on Wednesday.